All right, so this is going to be the answer key to the NMSI rotational motion multiple choice question. So let's go ahead and get started here. Let's see what it says. So number one says a bowling ball of mass m and radius r rolls without slipping down an inclined plane as shown above. The inclined plane forms an angle theta with the horizontal. Coefficient of static friction between the ball and the plane is mu s. Which of the following diagrams correctly shows the forces acting on the object? So we got number one here. Let's go ahead and draw it. Theta. There's a little ball guy right there. And it's asking for free body diagram. So, this is basic, pretty easy stuff here in Newton's laws. So it's in contact with a surface. So obviously there's a normal force. There's friction if the ball's rolling down the plane. The friction is going to be opposite, so that's going to be friction. And then there's weight, and weight is always straight down. So if I look at my answers there, it looks like answer matches up. Pretty easy, pretty straightforward on that one. Number two says, an automobile moves in a circle radius 110 meters with a constant speed of 33 meters per second. What is the angular velocity of the car about the center of the circle in radians per second? All right, so this is what we got. We got radius equals 110 meters. We got velocity, linear velocity is going to be 33 meters per second, and we want to know angular velocity. Well, again, our linear velocity equation is r omega. All I do is plug in here. Hold the screen. And I solve, and I get somewhere around 0.3 radians per second. That answer is going to be A. Again, that one was pretty easy, pretty straightforward there. We're rolling. Number three says, which of the following statements are true about an object's rotational inertia? Select two answers. All right. So let's go ahead and look at the possible answers. So rotational inertia is proportional to the object's mass regardless of choice of axis. So if we look at rotational inertia, look at it. Here's our equation. So let's see, doesn't matter axis, but mass. Yeah, well, mass is in there, so it seems like A is going to be true. Rotational inertia is inversely proportional to the object's speed. Equation has nothing to do with velocity or speed, so that's not true. Rotational inertia has the units kilograms per meters per second squared. That's not true. It's kilograms meters squared. Rotational inertia depends on the choice of the rotation of the axis. Yes, that matters because that's going to change your arm. So, answer is going to be A and B. Okay. We have 4. It says a wheel rotates through 10 radians in 2.5 seconds as it's brought to rest with a constant angular acceleration. What was the initial angular velocity of the wheel before braking? All right, this is straightforward. It's a rotational motion kinematics problem here. So we got, it went through 10 radians. It took in a time of 2.5 seconds, and it comes to rest. So final velocity is 0. We need to know what that initial velocity was. So we look at our equations, we see that we can do this equation. All right, and we just go ahead and plug in. It's a basic problem here. 10 equals 1/2. That's 0, it goes away. Time 2.5 seconds. I get my initial is going to be 8 radians per second. Answer. Next problem here, let's see. A solid disk has a rotational inertia that is equal to I equals 1/2 mr squared, where m is the disk's mass and r is the disk's radius. It is rolling along a horizontal surface without slipping with a linear speed v. How are the translational kinetic energy and rotational kinetic energy of the disk related? All right, so let's look at this real quick. So it's moving and rolling, so it's obviously going to have both. It's number 5, right? Yeah, number 5. So let's look at translational kinetic energy. Very easy. We'll label that as T equals 1/2 mass velocity squared. All right. Rotational kinetic energy is equal to the moment of inertia times the angular velocity squared. Now, let's go ahead and plug in for all this stuff here. Rotational equals 1/2. I is going to equal r squared, and omega is going to equal, well, omega squared, so you got to remember that squared is going to equal v squared r squared. All right, so r's are going to cancel out, so I'm left with ke rotational equals 1/2 times 1/2 is 1/4 mass velocity squared. Well, let's look at this. Are these exactly in the same terms? mv squared. This is a quarter, so there's going to be less rotational kinetic energy than translational kinetic energy. So that gives my answer. I think B. Yeah. Okay. 6. So the discs shown above are connected by a belt that rotates both discs at the same time. The belt does not slip as it rotates the discs. The discs have different radii as shown, with R1 being less than R2. What is the relationship between the angular velocities of the discs? All right, so we want to know what the relationship of the angular velocity. So how does their omega compare? So what this means, so what's key to this is, since the belt is driving both of them, they're going to both have the same exact linear velocity. Okay, so I can say linear velocity of 1 has to equal linear velocity of 2. Now we know the definition of linear velocity. It's omega 1 R1 equals omega 2 R2. There's our relationship, right? Is there an answer? Yeah, B. Answer. All right, clear that. 7. A wrench has 5 equal forces. All right, so equal forces V, W, X, Y, and Z apply to it. Which 2 forces produce the same clockwise torque? All right, so clockwise, so right away we can cancel out, if you're looking at the picture, Y is not going to produce any torque, and Z is actually going to produce counterclockwise, so Y and Z are out. So let's look at torque on V. So remember, torque is RF sine theta, but it's perpendicular there, so it's just going to be 1. So what do I got here? I know the force, so this is V equals, yeah, I said V, equals R, what's R, 0.2 times the same force. Force is the same. We should know right away that it can't be W. W cannot equal V because it's the same force but exerted at 0.4 meters away. So let's look at X real quick. X equals, torque equals RF sine theta. And in this case, the sine is 30 degrees. That's the angle to the axis. Well, sine of 30 is a half. You can plug it, if you don't trust me, you plug it in the calculator. So the radius there is going to be 0.4. In other words, double this. Force is the same times a half. Well, if that's double times a half, you're going to get the same exact torque. So it's going to be X and V. So the answer there, number 8, says a square piece of plywood on a horizontal tabletop is subjected to the two horizontal forces shown above. Where should a third force of magnitude 5 newtons be applied so that the piece of plywood is in equilibrium? So we want it in rotational equilibrium and translational equilibrium here. So if I look at this, 10 newton force, and this is a, so right now it's going to actually move up and rotate around. So to counteract that rotation, I could apply a force here, but that's not going to help my translational motion. So the only other place I could put a force to counteract that rotation of the 5 newtons is here, pushing back down on it. So that's going to counteract it rotating like that. So those cancel out. And if I got 10 newtons pushing down, I got 10 newtons pushing up, it's going to cancel out there. So let's see. I think the answer is A. Yeah. Answer. A door is free to rotate about its hinges. A force F is applied. Oh, let me change my page here. A force F is applied normal to the door, so that means perpendicular to the door, distance x from the hinges, produces an angular acceleration of alpha. What angular acceleration is produced if the same force is applied normal to the door at a distance 2x from the hinges? So we're going to remember that, oh, that was ugly. I'll do that. Summation of torque equals alpha, and that torque theta, but in both our cases here it's perpendicular, so it's just going to be that. So when I look at this, the only torque acting on the door is going to be the force. So what I got here is the distance is going to be x, force is that, equals the moment of inertia of the door is going to stay the same, and it's going to equal alpha. So it produces some acceleration alpha. That's what the problem tells us, right? This is what the problem tells us. So what it says is if I move the distance to be 2x, what has to happen to alpha here? So if I do the same thing, right? So I go 2x, the force stays the same. This stays exactly the same. The moment of inertia of the door stays exactly the same. So if these two stay the same and this here doubles, that means that the alpha doubles. What answer is that? So it looks like answer D. All right, clear. It says a bowling ball is thrown down the bowling lane, so it's initially spinning with a backspin and sliding forward at the same time. As it moves, how does the force of friction affect the ball's spin rate and the speed of the ball's center of mass? All right, so let's look at linear motion, velocity, and then let's look at rotational. So I have a ball here. Its velocity is this way. If the velocity is that way, we know that friction always has to draw opposite. So this is going to decrease velocity. Now, if I look at rotational, so the velocity is still this way, right? But let me draw this. It's doing backspin, so it's rotating that way. So that's going to be its omega. Well, which way did we draw friction? Friction stays the same. It's going to be this way. If I look at the point of contact and the force of friction is going that way, oh, whoops, stupid. That was stupid. Hold on, undo that. I was going to say, I'm getting the wrong answer here because I drew it wrong. That's not backspin. This is backspin. That is backspin. Sorry. It caught me off guard there for a second. So force of friction is this way. If I look at it, it's going to be opposite the rotation, right? It's opposite the rotation. I'm applying a force this way while the ball's rolling that or rotating that way. So it's going to cause my angular velocity, in other words, spin rate, to decrease. So spin slower, decreases. The answer there is going to be D. Sorry about that. And 11? Yeah. All right, so it says a uniform rigid bar of weight W is supported in a horizontal orientation as shown. So let me draw real quick. The rope. Okay, yeah. As shown above, by the rope that makes a 30-degree angle with the horizontal. The force exerted on the bar at point O, where it's pivoted, is best represented by a vector. So we're looking at this point right here. That's point O. What forces are acting at point O? All right. So let's think about what forces are overall. So the bar has weight, right? So in the center of the mass, right where I drew the arrow, it's going to have weight straight down. It's also going to have this force pulling this way. So since it's at it's suspended, right? It's at rotational equilibrium. We need to get forces to cancel that out. So right away, I know that this is going to break into. Let's see if I can change color here. All right, I can't figure that out. Go away. All right, so it's going to have a horizontal component of the force and a vertical component of the force. Get out of here. Okay, so we got to keep that in mind here. We need the forces to cancel out. So we're going to have a force vertical that compensates for the weight and the vertical component of that. All right, so well, it's gonna cancel the weight out with this involved. Does that make sense? So it's gonna be actually less than the weight because some of the rope is pulling it up, right? So these three verticals are gonna cancel out. So you need a force vertically going up there. Okay. Now you also are gonna have. So if I have a horizontal force right here going in, that means I need a horizontal force going this way to compensate. So my forces at this point are this way and this way. So in other words, my total force should be that direction there. If I look, that gives me an answer of B. All right, 12. A system of two wheels fixed to each other is free to rotate about a frictionless axis through the common center of the wheels and perpendicular to the page. Four forces are exerted tangentially to the rims of the wheels as shown. The magnitude of the net torque on the system about the axis. All right, so it just wants us to add up the net torque. So net torque equals. So let's look at all of the ones that are going counterclockwise, and we'll put those as positive. So on the drawing there, you have 1 on the inner circle, so R is going to be 2R times F plus counterclockwise, you got 3R times F, and you got another one, yeah, you got another one on the big circle, 3R times F. Only one that's going clockwise is going to be 3R times 2F. So that's all of them. Let's simplify here. I got what? 6, 8. So I got 8. Oh, this is stupid. That should be a negative because here it's the opposite direction. Minus 3. Oh, I'm sorry. It's 2 times 3. So that's going to be. Why am I scribbling? I can just erase. It's stupid. 6R, right? Because 3 times 2 is 6. So I get 2 net torque, and that's going to be B. I hope that helped. Pretty easy, pretty simple, pretty straightforward, but good review.